Today we're going to look at quantum mechanical model of the atom, and up until this point we've really been kind of focusing on the behavior of electrons in atoms and what we observe as emission or absorption spectra when atoms absorb and emit energy. So you've seen the flame test, the emission and absorption experiments. At this point, you should understand the range of wavelengths in the visible spectrum and be able to identify where that is and understand those values. And then with the equations that we've looked at, the energy equation and the speed of light equation, understand the relationship between wavelength, frequency, and energy. So at this point, we'll look at some of the peculiarities of the quantum mechanical model and the quantum numbers, which are going to allow you to be able to determine the electron configuration for many of the elements, most of the elements. So with the Bohr model, you should realize at this point that Bohr, his model was only able to accurately predict the energies for an atom that had one electron, and you saw that that could be an ion that only has one electron, or the hydrogen atom. That his model was very accurate for that type of atom, but beyond that, for an atom that contained more than one electron, it did not have the capacity to make predictions for those. So a couple of key components as we transition from Bohr's model to the quantum mechanical model. Energy is quantized, meaning that energy comes in these packets, or these allowable amounts of energy that were initially termed quanta by Max Planck, and eventually that was turned into photon in terms of light energy or electromagnetic radiation. The particle of light, or the carrier for that electromagnetic energy, is known as the photon, and photons of that radiation exhibit properties of both waves and particles, and this is what Einstein won his Nobel Prize for in his studies of the photoelectric effect, which is this ability of light to behave as a wave and also as a particle. So we'll see that that plays a big role in the quantum mechanical model here. And then energy has to be absorbed by an electron or by the atom in order for an electron to move to a higher energy level. That higher energy level is known as an excited state. And then when the electron drops down to what's known as its ground state, that is when we see photons emitted in the infrared range, ultraviolet range, and the visible light range, which you guys were able to actually see that in class. So this idea of particles behaving as waves and also as particles plays a key role in this idea of the quantum mechanical model. And again, Einstein's studies of light kind of helped pave the way for Louis de Broglie to apply this idea to the behavior of electrons and other particles. So Max Planck kind of initiated the study of light, the quanta of light, and photons of light. Einstein carried on those studies with the photoelectric effect. Both of those scientists focusing on the behavior of light and electromagnetic radiation. Louis de Broglie took those ideas and applied it to this behavior of electrons, where they were seeing this energy being emitted, and actually specific types of energy emitted by different elements. At this point, Schrodinger developed his model of the atom, and Schrodinger's equations were better able to predict allowable energies for an electron that has absorbed energy and emitting energy. And so this became the new model of the atom, the quantum mechanical model. And with this better model also came still more questions, despite the fact that Schrodinger was able to describe electrons as waves. There was still that wave-particle duality that existed, that had been confirmed through experimentation, that Schrodinger was not able to completely resolve this wave-particle duality. And both Einstein and Schrodinger had issues and were not happy with this wave-particle duality and this probability that played a role in the quantum mechanical model. So at this point, we're going to look at the quantum numbers and how the atomic orbitals are described by the Schrodinger equations, and try to give you a better picture of what these look like. And then we'll talk about a few more things about this theory, this model of the atom, including Schrodinger's cat. So the quantum theory basically assigns the electrons surrounding the nucleus to orbitals, which are mathematical devices, not like the elliptical orbits of planets in the solar system. So what that is saying is that each electron essentially has an address that's described by a math equation. Again, we're moving away from that planetary model that Bohr and Rutherford had, where you have these discrete circles or orbits around the electron where you're going to find around the nucleus where you're going to find the electron. So these are mathematical equations that described that probability, those regions in space of where you're able to find an electron. And so the orbitals have a characteristic energy or an energy level. There's a three-dimensional shape to it, and many of you have seen some of these shapes already at this point when you built your atom models. And each orbital is only allowed to hold 2 electrons, and these are some pretty key ideas, pretty important ideas within the quantum mechanical model. And these properties are all described by 4 quantum numbers, and at this point in the course we're really only going to look at 3 of the quantum numbers. We're not going to look at the 4th quantum number in any detail, and that has to do with what's known as electron spin. So the first quantum number describes the principal energy level, and this is a number that you've already seen with the Bohr model, where each of those rings of his model was defined as n equals 1 or n equals 2 as you went up in energy levels. So each of the principal energy levels is assigned a number, and the lower the number, so n equals 1 or n equals 2, the lower the energy level, the closer to the nucleus. Okay? Don't confuse this idea of low energy level with the idea about the amount of energy necessary for an electron to move to a higher energy level. So remember that in order for an electron to move away from the nucleus, if it's closer to the nucleus, it has to absorb more energy to make those initial leaps. As you get further away from the nucleus, it doesn't take as much energy for the electron to move from one orbital to the next. So closer to the nucleus is known as the lower energy level, but it still takes an enormous amount of energy to move, relatively, to move from a lower energy level to a higher energy level. So the first quantum number describes this principal energy level, and hopefully you're starting to realize that each of these numbers corresponds to a particular period in the periodic table, and we'll explore that in a little more detail later. The second quantum number identifies what's known as the sublevel, and this describes the shapes of the orbitals. So we've seen some of these shapes already. You've seen the spherical shape of the s orbitals. The lab that you did where you were dropping markers on a target and trying to simulate the probability of finding an electron within that 1s orbital, that was the spherical model of the orbital, and that's known as the s orbital. P orbitals have a different shape, and you'll see those near the end of this presentation. D orbitals and then f orbitals, and each of these also correspond to specific regions on the periodic table, which I'll give you more detail on that later. For now, you should realize that the sublevel, the second quantum number, describes the shapes of the orbitals. So the third quantum number identifies the projection of the orbital, which means the orientation of the orbital in three-dimensional space. Each sublevel contains one or more orbitals. So the s sublevel, it always contains one orbital. The p sublevel always contains 3 orbitals. The d sublevel will always have 5 orbitals, and the f will always contain 7 orbitals. And right now I'm just introducing you to these quantum numbers and what the numbers mean. Later on, we'll see the application of these numbers to the periodic table and how the periodic table is laid out. So at this point, you need to identify what each number is and what it tells us about the electrons and where they're found. So building on this idea, the third quantum number identifies the orbital. Each orbital contains only 2 electrons at most. So within an S sublevel that has 1 orbital, it will always only have 2 electrons. So anytime you see an S orbital, it's only going to contain 2 electrons. The P sublevel, which has 3 orbitals, which can be oriented in different ways in 3-dimensional space, can hold up to 6 electrons total if each of those orbitals has 2 electrons. The D sublevel, which has 5 orbitals, and again, each of these orbitals are oriented differently in space, in 3-dimensional space. The maximum number of electrons in a D sublevel will be 10 electrons if each of those orbitals has 2 electrons in it. The F sublevel with 7 orbitals can hold up to 14 electrons total. So this slide just shows you some models, some 2-dimensional pictures of what these regions in space look like, these 3-dimensional regions where electrons are likely to be found. And remember that these 3-dimensional regions represent where the electron is most likely to be found. It's not a guarantee that the electron is going to be in that position, but there's 90% probability that we'll find the electron here. So you can see the S orbital has that spherical shape. The D orbitals have that dumbbell shape, which you've already seen. And then the D orbitals start to get a little more complicated. You've got that clover shape, and then that last D orbital shows a torus with a dumbbell shape. And it's difficult to see in 3 dimensions here, but hopefully you can see that the orientation of each of these different orbitals is different. With the P orbitals, you can see the first one is oriented along the x-axis, where the second, that middle P orbital, is actually oriented along the y-axis, which would be coming out toward us. And then that third P orbital is oriented along the z-axis. And the same thing for the D orbitals, those would be oriented differently. So a couple other ideas that became a part of the quantum mechanical model is this idea of uncertainty. And Heisenberg introduced some equations to help describe this idea of uncertainty and the role it plays in the quantum mechanical model. And so this is known as the Heisenberg uncertainty principle. And basically what it states is that a particle cannot have a precisely determined position and a precisely determined momentum at the same time. There are some other properties of the electron where if you're measuring one property, you can't know the other property of the electron. And this uncertainty actually applies to all the particles, applies to protons as well. And so because velocity is proportional to momentum, the particle cannot have position and velocity simultaneously. And this idea of uncertainty was one of those conflicts that Schrodinger had with the model, and also Einstein was not settled with this idea of uncertainty, but this uncertainty helped better describe the behavior of particles within the atom. And so this idea of uncertainty and probability, again, it applies to all particles, not just the electron, but the electron is the one that we're going to be focusing on because it is responsible for the chemical behavior of atoms, and we'll be transitioning into bonding and those chemical properties of atoms that rely on the behavior of electrons. But this also applies to nuclear decay, and you'll see that you can't predict when a particular atom will decay, but you can determine the chance that it will decay in a certain period of time. So you can measure the probability of that decay, and we have some values that are pretty accurate about when so many of the atoms will have decayed. But you cannot precisely determine when one atom will go through a decay event. So the quantum world involves uncertainty, probability, wave-particle duality, And these are all ideas that could not be explained by classical mechanics or Newton's ideas of of how the world works. But it does very well describe the motion behavior of atoms in subatomic particles. So that wraps up our discussion of the quantum mechanical model and the quantum numbers.
But Mom, what about Schrodinger's cat?
Ah, yes, Schrodinger's cat. And so the cat. We will be saving this discussion for class, and so you'll have to stay tuned and be in class to know the story behind Schrodinger's cat.